All right, M1, if you were to do a free body diagram on M1, here you're going to have obviously FG going straight down, right? You're going to have FG going straight down. You're going to have F normal going straight up, okay? And FG1. And what's causing this M1 to accelerate forward is the static friction between M1 and M2. So I'm going to actually put the static friction right on this center. I mean, I could put it right here in the bottom, but it's going to look bad because it's already red. So static friction of M1 on M2 is what's causing this M1 to accelerate in the horizontal direction, okay? I think we already have that in the other page. Now, if we take a look at M2, this is where all the mess starts, I guess, right? M2, let me see what color I could make this. Let's make it blue. So, if we were to look at all the forces acting on M2, well, we definitely have this force right here pulling on this. So we're going to draw that force. So here's my force that's being pulling on this thing. And I will also have, right, FG2, and I would have F normal 1 pushing down against M2, right? So F normal 1 pushing down on it, okay? And I'm going to have F normal 2 going up from the surface there. And I will have two frictions. I have friction 1 from the top block to the bottom block going in the opposite direction. Here's my F friction 1. And then I'm going to have F friction 2, which is between the bottom block and the surface that it is being pulled. Okay. So this force F can be broken up into both Fx and Fy. So here's my horizontal component Fx, and here's my Fy. All right. All right. And this angle here happens to be 30 degrees. Okay? So if I were to take a look at this right here, M1, right? I have sum of all forces. I need a writing pad. So sum of all forces in the x direction is equal to m1a, right, in the x direction. Now this acceleration is same for both the top block and the bottom block because they're moving together. However, sum of all forces in the x direction, there's only one force, and that is the frictional force 1 that's causing that block 1 to accelerate in the positive direction. Okay? So here, if I set them equal to each other, m1ax is equal to, right, friction 1. But what is my friction 1? My friction 1 is equal to mu times F normal 1. As you know, my F normal 1 is going to have to be same as my FG1. If you were to take a look at sum of all forces in the y direction for mass 1 is equal to m1ay. And then sum of all forces in the y direction for mass 1 is equal to F normal 1, right, plus Fg 1, right? So you could say 0 is equal to F normal 1 minus Fg 1. So your F normal 1 is equal to just M1G, right? So you can substitute that M1G into my F normal 1 here. So my M1AX is equal to mu times M1G. And guess what? My mass 1's cancel out, and my A sub x is equal to mu. This mu is that's mu static 1 on 2, right? So 0.1 times 9.8, and I got my A sub x is equal to 0.98 meters per second squared. So A sub x was pretty easy. All right. Now let's take a look at this one. All right. If we were to look at the bottom block, M2, okay, there are a lot of forces involved in this. So here, if I were to look at just the x direction, okay, let's take a look at sum of all forces. So let's take a look at sum of all forces in the x direction. So sum of all forces in the x direction for my mass 2 is equal to m2 ax, okay? This ax is exact same as this ax that we calculated because they're going to be moving together as one. Then sum of all forces in the x direction for mass 2 is equal to, well, it looks like I have Fx, right, plus F friction 1 plus F friction 2, right? So if I set them equal to each other, my M2AX is equal to my Fx positive. I'm going to consider this direction to be positive. So my Fx minus friction 1, right, minus friction 2. Well, here, my M2AX now is equal to Fx is really nothing more than F cosine theta minus friction 1, which is mu 1 times F normal 1, right? We already know what F normal 1 is, by the way, right? Minus friction 2 is mu times mu 2 times F normal 2, right? Well, we're going to have to figure what F normal 2 is. We already know what F normal 1 is. That's easy enough. We know what mu 1 and mu 2 are. We're looking for F. We know theta. We know M2 and we know A. So this looks like the one we need to work on, right? So what can we do? Well, let's take a look at the y direction, okay? I'm going to box this one off as my equation 1, first equation for my mass 2, okay? Then, if we were to take a look at the y direction, so sum of all force in y direction for mass 2 is equal to m2 ay, right? And if I were to take a look at all the vertical forces acting on my M2, well, it looks like I have F normal 2, right? F normal 2 plus FG2 plus Fy, okay? And plus F normal 1. So here, 1, 2, 3, 4, 1, 2, 3, 4. So I got 4 vertical forces. Now, let's set them equal to each other. So here, I have M2AY is equal to F normal 2. That looks like positive, right? Because I'm going to consider up direction positive. That makes my FG2 negative. Right? That makes my Fy positive. And my F normal negative. F normal 1, that is. Now, you know Fy is F sine theta. You know Fx is F cosine theta. So we can substitute some of these things now with their relative values. So here, my normal, well, F force y2, mass 2, the acceleration in the y direction is 0 because it's not going to be accelerating vertically at all. So that is equal to, right, F normal 2 minus M2G plus F sine theta minus M1G. So if I solve for F normal 2, my F normal 2 is equal to, right, M2G plus M1G minus F sine theta. So I can actually substitute this. I'll call that equation 2, I guess. I could substitute this whole mess right into here, into equation 1. Then, what do I have? I have m2 ax is equal to f cosine theta minus mu1 fn1, right, minus mu2 times m2g plus m1g minus f sine theta. All right, now you can actually start putting some numbers in there, okay? Hopefully, the rest should be algebra for you. So here, m2, 20. ax, we already know it as 0.98. That is equal to f times cosine of 30, which is 0.866, minus mu1, 0.1, times f normal 1, which is 10 times 9.8, minus 0.2 times all this mess right here, right? 20 times 9.8 plus 10 times 9.8 minus f sine of 30 degrees. Oops, there's a hole in there. There's a pothole. All right. So if you work it out, I think you'll get something like 19.6 is equal to 0.866 f minus 9.8, right? And if I distribute this out, I'm going to get negative 39.2 minus 19.6. Right? This is half. 0.2 times half, you get 0.1. Right, so you get minus times minus, you get plus 0.1 f. So if you add the f's together, you're going to get 0.966 f, right? Minus this whole mess is 68.6, 19.6. So f comes out to, I believe, 91.3 newtons. All right. I hope that explains it. Is that good? All right. So what I'm going to do now is I'm going to actually hold you accountable for your homework problems from now until I guess Wednesday. I'll go over homework problems starting on Wednesday and then Friday. Okay. So you should be completing all your homework problems by now. So I'm going to finish up the note packets now. All right. So let's take a look at take a look at your note package, the rest of it. All right, so here we go. Vertical circular motion. Vertical circular motions is slightly complicated than the horizontal circular motion. Okay, so here consider a mass m, right, tied to a string moving in a vertical circle. Gravity is now in play, right? Use the radial and tangential axis as your x and y axis for this problem. Use radially inward as positive direction. So whether it is, when it's here, the radially inward is negative y hat will be the positive direction actually. Here, positive y hat will be the positive direction. Here, negative x hat will be the positive direction for the radial direction. Got that? So it's very important you keep your direction in towards the center as positive all the time. Okay? B, write down the Newton's second law for circular motion at each of these positions, right? So let's take a look at what happens at these different positions. Let's take a look at here at point A. I'm going to call this point A at the bottom. So here at A, right, how many forces are acting on this? Well, there are two forces. One is the tangent going this way, tangential force. And I have another force going down this way as my Fg. Okay? So here, this direction is the positive direction for A. Okay? That means this is my negative. So for part A, if you were to think about it, sum of all forces, I guess in the radial direction, is equal to ma radial. And we all know that is v squared over r, right? And there are two forces acting radially, and that is, right, tension and Fg. But we considered the radial direction to be positive, so m times v squared over r is equal to, and tension is in the positive direction, minus Fg. Okay? So this is important. All right. Now what about for part B? For part B, my tension is going this way. Here's my tension. And here is my Fg. My Fg now is going straight down, and it does not contribute any way of this object going in a circular motion. So it's very neutral in this case. It's very neutral, all right? Here, my gravity is fighting the circular motion. Here is very neutral, okay? So maybe you could write that down, right? Gravity is fighting circular motion, right? Fighting, fighting, right? It's fighting. So this is bad for circular motion. Here, gravity is neutral, right? Neutral, right? For circular motion. So, what would this look like? Well, for position B here, right? It looks like sum of all force radial is equal to ma radial, and there's only one force that's acting in the radial direction, and that is just the tension. So if you think about it, mv squared over r is just tension. Gravity doesn't come into play for part B. Now for part C, we have tension going down, right? Tension going down. And we have Fg going down. So they're both helping the circular motion. So in this particular case, in part C, right, gravity is helping, right, for circular motion, right? Okay? So in this particular case, the sum of all force radial is equal to ma radial, and sum of all force radial is equal to, I have tension and I have gravity. However, mv squared over r is equal to tension plus Fg in this case. Okay, tension plus Fg. So what happens? What happens when tension is the least? Like, let's say the tension is 0 here. What's making it go in a circular motion? It is the gravity that's helping to go in a circular motion. Okay? So at the top, there's no tension required to stay in the circular motion, right? As long as there's gravity there, right? So what's the minimum speed required? So what is the minimum speed required for the mass to have to go around in a circular motion? Okay? Without falling out of the circular motion at all. So if you're going a little too slow here, what's going to happen is right around here, it's going to flop out. It's going to go on this way. But at minimum speed, when tension goes to 0, it will stay in the circular motion. Okay, so that's what you want to figure out. If you go too slow, it's gonna stay out of the circular path. It's gonna just go. It's gonna come falling down like this way, rather than staying in a circular path. So at the top, so for part C, I guess, right? At the top, no tension is required. Right? Okay? That means if I were to take a look at this equation right here, right? mv squared over r is equal to tension plus Fg. But the tension goes to 0. So what happens? All I have is then mv squared over r is equal to just mg. Look what happens to my mass. My mass cancels out. So V minimum, this is minimum speed needed to go around the circular motion without a tension, is equal to square root of Rg. Right? So this is minimum speed needed to stay in the circular path, okay? If it's less than that, then it'll just like flop out of it. It's gonna go up, it's gonna flop out, and then it's gonna go straight. You know what I mean? So this is minimum speed needed to stay in the circular path without falling out of the circular path. All right. Alrighty. 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 So I think we're pretty much done, actually, right? So if you were to take a look at the horizontal circular motion example, right, static friction, right, speeding up, slowing down, and the net force on the coin. So if you were to look at a coin top of it like a record player going around, and let's say it starts to like, speed up, speed up, speed up. At a certain point, this coin is not going to be able to hold on to the friction because it's the friction that keeps this coin in a circular motion, right? So the friction has to act in towards the center of the circle. There's a certain point where this coin just like gonna lose it and just gonna slide off. Okay? So if you were to start the table spinning with no slipping, so the coin stays in place and spins along with the table, right? There's only one force acting, and that force, horizontally that is, that force is the frictional force. Of course, there's going to be, the Fg, right? There's going to be Fg, and there's going to be F normal too, right? So if you were to think about it, right? Sum of all forces, sum of all forces in the x direction is equal to MAC, because that's the radial direction. And sum of all forces in the x direction is just a frictional force. So mv squared over r is equal to friction mu times mg, right? You know F normal is going to be mg in this case. So look what happens to my mass. So the minimum coefficient of friction that you're going to need is going to be v squared over rg. So anything bigger than this value, it will stay at this speed, at this radius. Okay? Or if you want to calculate for what's the maximum, so V then is equal to square root of, right, mu RG. That's the maximum amount of speed that's going to stay for the coin to stay at this coefficient of friction. Julietta, you have a question?
Does heat, like with your frictional force, does the energy that you lose to heat count towards your like directional motion?
Heat. Um, well, heat doesn't have any direction, first of all.
Yeah, well that's what I'm saying. So like is that sort of lost energy in general?
I think the heat is only produced when there's a kinetic friction, but static friction, there's no heat generated. Static friction just
Okay.
keeps it on, stable, like stationary position. It's when you do work with friction by sliding across that generates heat.
So, but like, yeah, with our kinetic friction in our calculations, would we usually expect to like lose some to heat?
Yes, absolutely. And we're going to talk about that in chapter 8. Yeah.
Okay,
Yeah.
thank you.
Mm-hmm. All right. So when coin is slowing down, right, your friction is, less and less required to stay on the turntable. Okay, so um, you don't have to worry about falling it off. This thing falling off of the turntable when it's slowing down. All right. Now, when this thing does slide off, it's going to slide off, and it's sort of, I guess, that way. It's sort of going to get left behind, basically. It's not going to like fall off, as in like it's going to be shot off. All right. All right. For this one, I think we already know. Okay. We went over this thing, so make sure you pay attention to. This is embankment, right? This is not a inclined plane. This is embankment. Okay. So if it's going too fast, the friction has to act this way, right? The friction has to act this way. And if it's going too slow, the friction has to act this way, right? So make sure you can derive those two x and y for this scenario, and make sure you can derive this x and y scenario for when it's going too slow. Practice that, okay? I already showed you how to do this. You have this. So practice deriving this, because most likely you'll be quizzed on this. All right. So make sure you can derive this as well, please. Okay. So always derive what the safe speed should be, the design speed should be, given the angle and the radius of the turn. All right. So if you know the safe speed, then they will probably tell you to calculate the angle. But you could only do these with friction only if you know this design speed. Okay? If you don't know what this design speed is, then you can't really do this. Okay? So that concludes our chapter 6. Um, Now you need to do lots and lots of homework problems. And you really need to practice these homework problems. Because if you just see me do it, then it's going to make perfect sense because I usually do them correctly. And when you do problems correctly, it's going to make perfect sense. But it's when you have to do it on your own that's going to be trouble. So please make sure you practice them and get stuck. It's okay to get stuck. So when I go over it, hopefully I will unstuck you. All right. Any questions? So you should really do your homework all of them, every single problem. I'm going to try my best to go over every single one. I will also post the solutions of the homework up on Schoology, but you shouldn't just copy it. You should really just check on it. All right, so I'm going to stop my lecture here.